Welcome back, everybody. We are going to take a look at example 3 together. And this is on page 102 of the workbook. This is going to be the first of a few examples where we use the fundamental theorem of calculus to calculate a definite integral. Okay, so let's remind ourselves just of what the fundamental theorem said again. It said if you want to take the integral of a function, what you need is an antiderivative, capital F, and you're just going to evaluate that antiderivative between a and b. So the key is being able to find an antiderivative for a function. So that's how we're going to start this problem. So we need an antiderivative for the function sine of x, and remember, earlier on this page we had a big long discussion about antiderivatives of common functions. So let's sneak a peek at our table above here. I'm going to just scroll down. And you'll notice that I've numbered the formulas just so that we can tell them apart a little bit more easily. And we have formula number 4 tells us that an antiderivative for sine of x is negative cosine of x, and so that's going to be our starting point here in doing this problem, is to just write down that antiderivative. Okay, and there's a special piece of notation just so that we don't have to keep writing f of b minus f of a over and over again. What we can do is write a bar, 2 pi and 0, and what that means is negative cosine of x evaluated between 2 pi and 0. So that bar just means we're going to evaluate negative cosine of x between 2 pi and 0 and subtract them, just like this statement over here says. Okay, so let's do that. So we'll first substitute in the 2 pi. There's our upper limit, and then we'll subtract the lower limit, which is negative cosine of 0. Again, that bar is just a shorthand notation for doing what we just wrote down here. And it comes down to asking ourselves, can we remember what the cosine of 2 pi and 0 are? Okay, well, you might remember from trig that cosine of 2 pi is 1, and cosine of 0 is also 1 because 0 and 2 pi are the same angle on the unit circle. So what do we get here? Well, we're going to get negative 1 minus negative 1. Notice that those add up to be 0. So if we've done everything right, the value of this integral is 0. Okay, now just to reassure us that we got a correct number here, let's see if we can convince ourselves graphically that that's the correct number. So we just integrated the sine function from 0 to 2 pi. And if you graph the sine function from 0 to 2 pi, it kind of looks like this. Okay, so here's 0 and here's 2 pi. What does it look like to you the value of the integral should be? Well, the integral should add that area that I just shaded, and it should subtract the area that's below. And so because those two areas are equal, it makes sense that we should get 0 out of this integral. Okay, it kind of confirms the answer that we got here. Okay, well, this is kind of a short example, so why don't we go ahead and try another example on the next page, example 4. Same type of question, just a different function. Okay, so suppose that we want to integrate 4x plus 1 plus 2e to the x from 0 to 3. The steps are going to be exactly the same here. So we'll start with the function that we're integrating. First step is to find an antiderivative for that function. In this case, we've got a few different pieces, so we can maybe tackle those pieces one at a time, starting with the 4x. Could we write down an antiderivative for that? Well, 4 is just a number, so we'll factor that out. And what about an antiderivative for x? Okay, well, that comes down to the power rule. And I apologize for scrolling, but I'm going to do it one more time. Okay, if we want an antiderivative for x, we can look at this first formula on our list up here. The power rule told us that if you want an antiderivative for x to the n, you're going to raise the power by 1 and you're going to divide by the new power. That's what that x to the n plus 1 over n plus 1 says. All right, so if we come down and apply that power rule to x, which is really x to the first, we're going to get x to the second over 2. We raised the power of x by 1 and we divided by the new power. Okay, so there's the antiderivative of the first term, and then we move on to the 1. What would an antiderivative of 1 be? That's just going to be x, because the derivative of x is 1. Okay, and then finally, what would an antiderivative of 2e to the x be? Well, we talked about how e to the x is its own antiderivative, so antiderivative of 2e to the x is going to stay the same, 2e to the x. Okay, so there's our antiderivative, and we need to evaluate that between 3 and 0. Okay, so let's maybe do a little simplification before we do that. So 4 over 2, we can simplify that down into just 2. That looks a little bit nicer, and now we'll go ahead and plug in our 3 and our 0. Okay, so take our antiderivative and evaluate it at 3. So substitute a 3 in for every single x. There's our upper limit, minus, plug in a 0 for every single x. Okay, and now it's a matter of just doing the arithmetic and seeing what we wind up with here. Okay, so let's see, 2 times 3 squared, that's 2 times 9 is 18, plus 3 is 21, plus 2e cubed. Okay, and over here we get some terms that go away. Okay, those are 0, and we have to subtract 2e to the 0, but what's e to the 0? That's just 1. So we've got 21 plus 2e cubed minus 2. And if you combine like terms, the 21 minus 2 is 19, so we're going to get 19 plus 2e cubed, and that should be our answer. That's the value of this definite integral.